So we're gonna start this example by reading the problem. A hot air balloon rising straight up from a level field is tracked by a rangefinder 500 feet from the liftoff point. At the moment the rangefinder elevation is pi force, the angle is increasing at a rate of 0.14 radians per minute. How fast is the balloon rising at that moment? So let's assume that we have a liftoff point. I'm going to just make that point here. And that, of course, is going to be on the ground. And then there's like a balloon up here. And there's some tracker guy kind of looking at that balloon over here. And so the balloon is rising directly up. So let's see if I can get a straight line going here. Okay, so that balloon is just going straight up from the liftoff point, and then the tracker person is looking at it from over here. Okay, so this is your balloon, this is your tracker, this is a liftoff point. Clearly that creates a right angle, and then there's an angle of elevation, which is the angle between the ground and the line of sight, and that's theta. So that's the picture we have. So if it's rising straight up from liftoff point, that's just a nice vertical line, and the tracker is 500 feet from the liftoff point. So that means that our tracker is going to be 500 feet from this point to the tracker right here. So this is 500. Now the tracker is never going to move. So this piece of information is constant. It's fixed. So we're going to be able to use that in an equation. Okay. At the moment the rangefinder's elevation angle is pi force. So what's going to happen is as this balloon goes up, this angle is going to change. But at the moment when that angle is pi force, so that means that at some moment theta will be pi force. And remember, theta is a variable. It's just, that's usually what we use for angles is theta. So that's why I'm using theta right now. At that moment, the angle is increasing. Angle increasing. That's a rate. At a rate of 0.14 radians per minute. So if theta is the angle, then the rate of change of theta is d theta dt, which is 0.14 radians per minute. Okay? How fast is the balloon rising at that moment? So how fast is the balloon rising? Again, the question is a rate, fast, balloon rising. Well, we said the 500 feet doesn't change, and the balloon rising is talking about the distance between the balloon and the ground. So we're going to go ahead and call that y. Now we could assign a variable to the distance between the balloon and the tracker, but if you look at the problem itself, the problem gave you an angle and it gave you a rate of change of angle. It never said anything about the line of sight. So we don't really have a lot of information about this piece. All our information has to do with an angle. So we're going to try to focus on that because that's the information we were given. Has to do with the rate at which the balloon is rising, which involves y, and this angle. Okay. Okay. So Pythagorean theorem is usually what we use with right triangles, but if I use Pythagorean theorem, I'm going to involve the 500, the y, and the line of sight, and not the angle. So Pythagorean theorem isn't going to really do us any good here. We're going to have to think what relation will involve a y and a theta. And yes, you probably started thinking that this is going to involve trigonometry, given that we're using angles, and that's true. So I'm going to ask myself, which of the trig functions involves the angle, the opposite side of the angle, and the adjacent side of the angle? Because those are the two quantities that I either have or am looking for. And opposite over adjacent, so katoa, opposite over adjacent is sine. So we're going to use, to build the equation, we're going to use sine. And that just means that it's going to look a little different than before with Pythagorean theorem, but it still works because it's true that the sine, of theta, the sine of theta, is in fact equal to the opposite side over the adjacent side. Okay, I'm going to scroll down here a little bit. So this equation is true. It relates theta and y. So we're that's good. We're like step 3 now. We need to go to step 4, which means take the derivative with respect to t, and that's what we're about to do. But I'm just going to remind you, this looks like a quotient. It's really 1 over 500y. To make this even easier, I'm going to go ahead and multiply both sides by 500 before I take the derivative, because fractions are sometimes scary. I don't have to do this, but I'm going to, because it's going to make the derivative just a little bit easier for me to work with. So I'm going to take a look at 500 sine of theta equal to y. Those 500s went away. And now, remember, and I guess I never stated it. I was given d theta dt, and I'm looking for how fast the balloon is rising, and that rate is called dy dt. All right? Now, I'm going to go ahead and take the derivative of this equation in terms of t. Remember, theta is a variable. So when I take its derivative, 500 times sine of theta is simply 500 times cosine of theta, derivative of the outside, leaving the inside alone, times the derivative of the inside, which is d theta dt. And that's okay, because d theta dt was given. And that is going to equal the derivative of y, which is dy dt. And so far everything's looking good. I have a d theta dt. I'm looking for a dy dt. But what about that theta? Oh yeah, that was given. It's just pi fourths, so no need to worry. We have everything we need. We'll just switch colors here and go that dy dt is going to equal 500 times the cosine, oops, that's a big C, times the cosine of pi fourths times negative, or excuse me, 0.414. Times 0.14. This is kind of multiplication here. And then once I figure that out, that'll be my answer. Now, cosine of pi fourths is square root of 2 over 2, but since there's a decimal, I'll go ahead and run this with the calculator and get a final answer. And I did this on a regular scientific calculator, and I was able to get basically 50 as my answer. But I'm going to go back to my units and ask myself, all right, 50 was in terms of, let's see, scroll up a little bit so I can see that. It's feet. So that's going to be 50 feet per minute. And that's it. So this is an example involving an equation that dealt with trig, and hopefully that kind of made sense. So go ahead and put that in your notes, and then we'll watch the next one.